Welcome to part 6. In this, we'll focus more on further learning and resources. We're going to go through a couple of topics. The first one is advanced topics and future directions. And in this advanced topics, we're going to first talk about generative adversarial networks or GANs. Generative adversarial networks are a class of deep learning models introduced by Ian Goodfellow and his colleagues in 2014. GANs consist of two neural networks, the generator and the discriminator, which are trained simultaneously in a competitive manner. As you can see from the names, the generator learns to produce synthetic data samples that are indistinguishable from the real data, while the discriminator learns to differentiate between real and fake samples. So to go over some of the overview of GANs, GANs are composed of two neural networks, the generator and the discriminator. The generator generates synthetic data samples from random noise. The discriminator evaluates whether a given sample is real from the training data or fake generated by the generator. The generator and discriminator are trained simultaneously through adversarial training. That's why it's called generative adversarial networks. The architecture of GANs has the generator, which we already know, that takes random noise as input and generates synthetic data samples. The next one is the discriminator, takes real or fake data samples as input and predicts whether they are real or fake. The generator and discriminator are typically implemented using deep neural networks such as multi-layer perceptrons (MLPs) or convolutional neural networks (CNNs). For the training procedure, it's 3 steps. First is initialization, where you initialize the parameters of the generator and the discriminator networks. The next step is adversarial training, where the generator generates fake sample from random noise. The discriminator classifies both real and fake samples as real or fake. The generator is trained to produce samples that fool the discriminator, maximizing the probability of fake samples being classified as real. The discriminator is trained to correctly classify real and fake samples, minimizing the probability of misclassification. And the third step, optimization, is where you update the parameters of both networks using backpropagation and gradient descent based optimization algorithms. One of them is ADAM. The next we'll talk about is loss functions. Now for the generator loss, it measures how well the generator fools the discriminator. It is typically the negative of the discriminator loss on fake samples, whereas the discriminator loss measures how well the discriminator distinguishes between real and fake samples. It is the sum of the losses on real and fake samples. Next topic is about common variants of GANs. There are 4 of them. One is the deep convolutional GANs, which is DC GANs. GANs with convolutional neural networks in generator and discriminator, commonly used for image generation tasks. Next one is conditional GANs or CGANs. GANs conditioned on additional information such as class labels to generate samples with specific attributes. Next one is Wasserstein GANs or WGANs. GANs with the Wasserstein distance-based loss function, leading to more stable training and better sample quality. The last one is the cycle GANs, which is GANs used for unpaired image-to-image translation task, learning mapping between 2 domains without paired training data. The applications of GANs include image generation, where you generate realistic images of faces, objects, scenes, etc. You've probably seen some of those online these days. Image-to-image translation, translate image between different domains such as day to night, black and white to color, etc. Style transfer artistic styles between images, more like a signature of an artist. Data augmentation, where generate synthetic data samples to augment training data sets. Anomaly detection, detect anomalies in data by generating samples and identifying deviations from the training distribution. Generative adversarial networks have revolutionized the field of generative modeling and have applications in various domains, including computer vision, natural language processing, and healthcare. However, training GANs can be challenging due to instability and mode collapse issues. requiring careful design choices and training strategies to achieve good performance.